Hi all, my name is Flynn Darby, and today I'll be presenting to you on active neutron multiplicity counting of kilogram quantities of highly enriched uranium. I'd like to thank the consortium for hosting this workshop and my collaborators and advisors from the University of Michigan and Los Alamos National Laboratory for helping me with this work. To start us off, the measurement campaign I participated in was the Measured Uranium Subcritical and Critical Configurations campaign, or otherwise known as MUSIC. It's hosted by Los Alamos National Laboratory through the NSERC, or National Criticality Experiments Research Center, where the main purpose was benchmark critical measurements to compare to previous critical measurements for nuclear data purposes and other validations. We also looked at neutron noise techniques for these large, highly enriched uranium assemblies. And specifically, I want to talk about neutron multiplicity counting, or NMC. NMC provides the activity and quantity of fissionable and fissile material, and it's useful in safeguards and criticality safety. You can see on the top right there, a snapshot from our experiment showing the top of an HEU shell set we were measuring and a couple of our detection systems. And on the bottom right, you can see myself on the left and one of these Los Alamos scientists on the right working the remote detect or measurement system. So why do we do multiplicity counting, especially in this consortium? The IAEA, or the International Atomic Energy Agency, declares a significant quantity of HEU as 25 kilograms. If anyone has this much material of HEU, they could possibly use it as a weapon. And in this set of measurements, we look at configurations from 10 to 60 kilograms of HEU. So being able to identify those signatures is important for safeguards purposes. NMC also estimates the sets of parameters of special nuclear material and verifies the declared amounts, which is crucial to avoid diversion scenarios. If we can't verify the exact amount, there are different scenarios where material could be diverted for clandestine purposes. For the experiment, we were again at the National Criticality Experiments Research Center, or NSERC. We were measuring the rocky flat shells, which are 93% uranium-235, and we placed a californium source at the center of our assembly to interrogate the HEU, since it doesn't fission much on its own. The assembly you can see on the top right, the bottom and top halves on the right and left, respectively. The scientists in the room would work together to stack these shells on the planet critical assembly platform. You can see on the bottom left an example of one of the scientists working with the shells spread out on a cloth to change our configurations. We had to spread out cloth for each configuration because the uranium flakes very easily and we don't want it contaminating the room. Also wear wet respirators as well so that you don't get any particulates in your lungs. On the bottom right, you can see the photo of my detection system measuring the assembly, as well as one of the scientists calibrating our systems. I measured with the Oscar, which is a 3x4 organic scintillator array of 2x2 inch trans steel beam detectors. We used it to measure tens of kilogram configurations of these rocky flat shells. And I used pole shape discrimination to discern my neutron detections. We conducted NMC on the detected neutron pulses using a set gate width and random trigger gating method. And I used a well-known 3-parameter model to estimate the singles, doubles, and the triples from our experiment. A little more on the experiment. I was measuring 166 centimeters from the center for a minimum 60-minute measurement per each configuration. We were measuring the rocky flat shells again with my 3x4 array. And I went ahead and simulated each of these configurations with MCMP 6.2 to estimate the leakage multiplication and the effective criticality for each configuration, and simulated detector response in MCMPX Polemi. If you're not familiar with leakage multiplication, it's a quantification of, for every neutron released in our assembly, how many leak out. And the K effective is a quantification of, for every neutron that's born from one fission, how many go on to cause a subsequent fission. For our data, I had to apply pulse shape discrimination to tell the difference between neutron and gamma radiation, since we're only concerned with neutrons here. You can see an example of some pulse shape discrimination plots for my measurement. The top band is the neutrons that have a high tail to total ratio on each pulse, and the bottom band is the gammas, which have a lower ratio. I can discriminate this data going by light output slices or energy slices on my detector. And I can take a significant upper bound to my gamma distribution and take everything above that as neutrons. You can see on the PSD plots for a lower configuration, which still had a K effective of 0.91 and 40 kilograms of HEU, that we had a significant neutron band, but the relative intensity increased very significantly for the neutron band for our close to critical configuration below. And we also experienced some pulse pileup, but you can see the color scale here is on a log scale. So the relative magnitude of our pulse pileup is very low in comparison to our true band. Some preliminary results I acquired from my discriminated neutrons using a set gate width of 1 microsecond are shown here. You can see how the singles, doubles, and triples increase with the HEU mass. The singles rate, we saw some saturation at our highest configurations, but the doubles and triples still increased very clearly for all the configurations. We were collecting full waveforms, so that was an issue. At our closest to critical configuration, we ran into data throughput issues. But for our lower configurations, specifically the first three, we estimated the leakage multiplication using these singles, doubles, and triples with a very high accuracy. For the third to sixth configurations, our estimates diverged. We were using MCMP 6.2 K code to estimate the leakage multiplication based off the K effective value, and then also an F1 tally in 6.2 of the leaking neutrons out of the system to take as our true leakage multiplication. Future work is being done on which is the most correct comparison, but despite that, taking a look at configuration 3 through 4, we were still bound by these simulated estimates. For the last configuration, we clearly were saturated as we're heavily underestimating the leakage multiplication compared to both our simulation estimates. The expected impact for these measurements is it's the first NMC with the safeguards focus on large quantities of HEU using our organic simulators. And it's NMC of bulk HEU can provide experimental comparison for a recent publication on multiplicity theory beyond the point model, and also justifies continued use of our organic simulators for measurements at the NSERC and elsewhere. The broader MTV impact keeps our group at the University of Michigan closely connected with NEN2 at Los Alamos, and we'll continue to collaborate with LANL and NSERC and elsewhere. And it's also inspired in my research some new system designs for plutonium samples, also in collaboration with Los Alamos. Some conclusions we can make off the results are, again, the first time we've done neutron multiplicity counting for HEU configurations this large. And we've gotten very precise measurements of the multiplets and decent estimates of the leakage multiplication. This justifies further use of organic scintillators for these types of neutron noise measurements, and we can truncate our data throughput by collecting in list mode on a later occasion. But some next steps are to better understand our measured response by simulating our detector response in MCMPX buliming. And we'd also like to use this data set to compare to multiplicity theory beyond the point model. And we would also like to look at coupling of our interrogation source and the samples. Previously, it's been shown for low leakage multiplications less than 2 that the coupling and leakage multiplication strongly correlate despite the composition of your highly enriched uranium or the shape. So looking at this relationship for these large leakage multiplications could allow us to estimate sample masses with this invariant coupling. And with that, I'd like to acknowledge the consortium, DOE, and Los Alamos National Lab for all their help with this project. Thanks so much for listening.